Welcome back to Logic, Language and Information, and to this, the first in a series of lessons on propositional logic programming. This lesson will give some historical context to the enterprise of automated reasoning, of getting computers to think logically. The subsequent lessons will delve further into logic programming using a logic-based programming language called Prolog. So let's begin. First, a big picture view. Computers have profoundly changed the world over the last 50 years, so an educated person today needs to have at least a basic conceptual understanding of computers, as well as some practical knowledge of how to use them. As everyone knows, computers are based on logic. What is less well understood is the multiple layers which make up that truth. At the level of physical stuff, the hardware of computers is composed of digital electronic circuits. The basic building blocks of digital circuits are AND or NOT gates, which are physical electronic realizations of the connectives of propositional logic. The application section 3 on combinational digital circuits gives an introduction to this core class of digital circuits and their grounding in logic, and more generally, an introduction to the discipline of electronic engineering. At the level of thinking and doing stuff, the software of computers is the means by which we get to use the computing capacity of hardware. Logic is fundamental in multiple areas of computer science, the home discipline of software. Logic is central in giving the formal meaning or semantics of commands and declarations in programming language. Indeed, the idea of a formal language with syntax generated by a grammar first emerged in logic. The analysis and design of programs, database systems, even operating systems, all of these draw on formal logic in various ways. The area of computer science within which logic is most visible is that of automated reasoning, which falls under the broader area of artificial intelligence. In trying to program a computer to think logically, the core job is to compute logical consequence. The knowledge available to the system should not be restricted to just the propositions explicitly stored in the computer, but should ideally include all the logical consequences of those stored propositions. This sequence of lessons on propositional logic programming will provide an introduction to the enterprise of automated reasoning and how to compute logical consequence in a fragment of propositional logic using a programming language called Prolog. But first, some historical context. The computational aspects of reasoning have a surprisingly long history. Going back to the 17th century, the English philosopher Thomas Hobbes first formulated the radical idea that human reasoning, or ratiocination, is a process of computation, involving a form of addition and subtraction of concepts and propositions. These days, Hobbes is better known for his political philosophy, notably the view that in the absence of a social contract binding us together in a political community, human life in a state of nature would be solitary, poor, nasty, brutish and short. In Hobbes's own era, his views on the computational nature of reasoning were strongly endorsed by the next in our cast of historical figures, Gottfried Leibniz. The 17th and 18th century German philosopher and mathematician Leibniz made the ambitious proposal of a universal symbolic language, the Characteristica Universalis. Leibniz's central idea was that concepts expressed in natural language are complex derivative concepts, and that by assigning symbols to all primitive, irreducible concepts, one could then formally express complex concepts as combinations of symbols for primitive concepts. Now, this was all 200 years before the first formal language presentations of propositional and predicate logic. And in Leibniz's time, logic was more a loose grab bag of principles. Leibniz's ambitious dream was that his universal language would be a means by which disputes between persons could simply be resolved by calculating or reasoning. Coming now to the beginning of the 20th century, in the midst of a great surge of progress in formal logic, the German mathematician and logician David Hilbert proposed a meta-mathematical program of research. It was aimed at resolving once and for all a crisis in the foundation of mathematics posed by paradoxes and inconsistencies discovered in the late 19th century. The program was an attempt to show that all of mathematics follows from a correctly chosen finite system of axioms, and that some such axiom system can be shown to be provably consistent. My PhD advisor's PhD advisor's PhD advisor was David Hilbert, so I'm a fourth generation intellectual descendant of him, so I'm a bit of a fan. To establish the consistency of more complex parts of mathematics, one should be able to, according to Hilbert, bootstrap up from the simpler areas of mathematics, such as arithmetic on the natural numbers. Alas, Hilbert's dream came to a crashing halt only 11 years later, in 1931, at the hands of a then 25-year-old fresh PhD, Kurt Gödel. Gödel proved that any formal logic system expressive enough to describe arithmetic on the natural numbers, 1, is incomplete if it is consistent, and 2, the consistency of the system cannot be proved within the system itself. Recall that incompleteness means that there exist true formulas of the language that cannot be proven by the rules of the proof system. Key ideas from Gödel's incompleteness theorem were incorporated into the work of the young English mathematician and logician Alan Turing, who is the true founder of the computer age. Turing formalised concepts of computation and algorithm with his logical computing machine model, subsequently called the Turing machine model. Turing's 1936 paper on computable numbers directly built on Gödel's result to show that it is not possible to decide algorithmically whether or not a given Turing machine will halt or successfully terminate on a given input. To prove the result, Turing developed a model of a universal Turing machine, which could simulate the computation of any Turing machine on any input. It is the universal Turing machine that served as a blueprint for the construction of the first stored program digital computer by John von Neumann in 1946. After spending World War II decrypting German code for the British military, Turing went on to make foundational contributions to the field of artificial intelligence. Turing proposed a test of a machine's ability to exhibit intelligent behaviour equivalent to or indistinguishable from that of a human. Think of text-based chat rooms on the internet, where you enter some text and get some text replies only. Could you tell if your interlocutor was actually a computer rather than a person? And how would you tell? Turing predicted that by the end of the 20th century, the phrase machines thinking would be commonplace. Regrettably, Turing did not get to see the world-changing consequences of his work. He died in 1954 after being prosecuted and persecuted for homosexuality. Our interest in this sequence of lessons is on logical reasoning performed by a computer. As we've already noticed, in trying to program a computer to think logically, the core job is to compute logical consequence. We would like a yes or no answer to questions about whether one formula is a logical consequence of another list of formulas. Recall that logical consequence is a truth-transferring relationship. It requires that under all ways of valuing the atomic formulas, if A1, A2 up to AN are all true, then B must also be true. We might think that in propositional logic, this cannot be too hard. After all, Gödel-like incompleteness results occur at the next level up, in predicate logic and its extensions. But as we know from truth tables, there is an exponential growth in the number of ways of valuing the atomic propositions, so an explicit check of all of them is dumb and impractical. We'll see an example with 64 atomic propositions in lesson 6.3. 2 to the power 64 is more than 18 quintillion, where a quintillion is 10 to the power 18. We definitely won't be doing truth tables there. Indeed, there is $1 million available if you can devise a better method for deciding propositional logical consequence. Specifically, a method that is polynomial rather than exponential growth in the number of atoms. That problem is equivalent to a fundamental problem in computer science, the P versus NP problem. While still unsolved and prize unclaimed, many researchers believe the answer is no, that P does not equal NP, and therefore no polynomially bounded methods for computing logical consequence are to be found for propositional logic. As presented in the core lessons on propositional logic, the proof tree method does give us an alternative to truth tables as a means to establish logical consequence, because the method is both sound and complete. However, it is not great for computers. Remember how much choice you had in applying the tree rules, how making a poor choice could lead to a blowout in the size of the tree. It is this that makes implementation of proof trees in a computer program rather difficult. Although there are implementations out there, usually a variant of proof trees called Tableau are used instead. To find decidable and practically computable classes of logical consequence problem, many researchers have gone down the path of shrinking the playing field with various restrictions. The first is to restrict the language. Instead of all possible formulas, restrict instead to a manageable fragment. For the rest of these lessons, we will be dealing with program clauses and goals, which fall into a class known as horn clauses. The second restriction comes as a follow-on from the first. By using only simple formulas of a known shape, we can get to work in a proof system with only one rule, to keep it simple for dumb machines. Logic program is a direct declarative style of computer programming using logic-based languages such as Prolog or Datalog. This brings us to the end of this lesson introducing logic, computers and automated reasoning. In the next lesson, we'll get stuck into logic programming in Prolog.